And we're off. So welcome to week 3. I just did the head count, 23 people are here today, just for the record so I know. So this week we're mainly going to be focusing on rendering, which is a kind of fancy way of saying graphics, and some specific parts of graphics that are going to be relevant to the course. But before I get into that, I want to talk about something more general that's very relevant to games, and that is the idea of a main loop. In fact, hold on a sec, I should put this into play mode. Let me get out of this. Sorry, amateur hour here. That was the wrong thing I clicked on. No, how embarrassing. Alright, let's try that again. The main loop. Is that a phrase that already means anything to anyone? If we talk about a main loop in a game or an app? Yeah, some of you. Okay, fine. So it's not super sophisticated, but it's a kind of an obvious entry point that we have to discuss. So in order to get into that, I'm going to start with a question, and that is, what are games? It's a bit of a rhetorical question, maybe a bit too vague to invite an immediate answer, so I won't bother asking you. But when we think about computer games, I tend to think of them as being a special case of a more general and slightly more legitimate thing in computer science, and that would be simulations. You take the general idea of simulation in computer science, where you're maybe modelling, simulating the weather, or you're simulating traffic flow in an urban environment because you want to see what will happen if you, put in a new road layout, or you change the timing on the lights or something. You do all sorts of things where you do simulations. So the general idea is that you've got some kind of virtualized world running inside the computer for some purpose. There's some questions that you as a human want to ask about the world or the fictionalized copy of it that you've put inside the computer, like, what will happen if I do X, Y, or Z? Or maybe you're just doing it for fun as well. And that's what games are. I would say games are a type of recreational simulation project. Interesting thing about the kind of games that we're going to deal with in this course is that they're generally real-time. Obviously, that's not universally the case. You get games like, chess or something. It's certainly a game. It's certainly something you can get a computer to do, but it's turn-based. So the way you think about that is a little bit different because it's just a case of, I move, then you move, then I move. But real-time games have got this additional complication that even if you're not doing anything, stuff is happening. So the game isn't waiting for you all the time. If you want to do things, it might well let you do them. But even if you're inactive, the world is still ticking behind the scenes, and that's an important distinction. Okay, so we've said that games are simulations. We want to see what simulations are. I've already told you, kind of. Imaginary worlds running inside the computer, subject to well-defined laws. I say but potentially crazy because for a lot of simulation projects, you maybe want accuracy. You are trying to capture some real-world behaviour. So you go out and you do observational science or something. You measure stuff about the world, and then once you've got that, you encode that in the program to create a reasonable copy of it. But you don't have to do it that way. And in the case of games, you often don't. For example, although modern games often have quite good physics systems inside them, the primary concern is not realism. If your concern is fun, so the vehicles tend to have they behave very nicely, but their handling is very exaggerated. If you look at it carefully, the kind of gravity levels are not the same as in the real world or in first-person shooters. The way that the speed at which you can run about and accelerate, completely unrealistic. You couldn't do it in real life; it would kill you. But we do it in games because it's just conventions were established, and we thought it was fun to do it that way. But the fact is that even if the laws aren't realistic, they are still laws. They are obviously encoded in the program. They're just the laws of some fictional universe. So one interesting thing about simulations, because of this idea that it's an imaginary world, and the imaginary world is full of stuff, things, and the things are kind of going about doing whatever it is they do, obeying their own laws in life. If you've got like pedestrians in a simulated city, they have places where they want to go and they have to get there and they're doing their thing. So they've got this kind of internal agency to them. That makes them quite a natural fit for thinking of them as objects. And indeed, object orientation actually came out of this. There's a kind of little bit. Does anyone want to hazard what is the first object-oriented programming language? Does anyone happen to know? What do you think?
Is it Smalltalk?
So Smalltalk is a great answer, and that's a totally legitimate claim. And some people would say that it is indeed Smalltalk. Anyone heard of Smalltalk? Okay, it's become obscure now, but it's actually a really interesting language developed in the 1970s. But it itself could be argued as being maybe the second object-oriented language. The first one was done in 1967, and it was called Simula, and it was for writing simulations. And the Smalltalk people kind of borrowed some of the ideas from Simula and developed them into more what we would think of as object orientation now. So it turns out the whole simulation field and object orientation are quite tied together. Yep. So that's the story there, that this language, which I think was a bunch of Danish guys actually came up with Simula, and they used it to write early simulation projects, because it turns out they thought it was a natural way to think about that type of problem, instead of thinking about it in the kind of conventional sense of, merely procedures that operate on data structures and data comes in and data comes out. They thought, no, this idea of kind of objects that kind of contain their own data and can do things that interact with each other was a way of thinking that they thought was appropriate for simulations. Right, so here's an actual main loop, but this is written in a kind of a sort of conventional procedural style, if you like. But it's very simple. The idea is you've got a function somewhere in your game. Let's just call it main loop. And here's the loop part. You've got a while loop, and this just keeps going while the game's running. So this is, true almost always until the very end when you press quit, and then that flag gets changed and you fall through and actually shut down the app. But basically, while you're running the game, you do these three things. Now, other people might frame this differently to the way I've done it, but this is a fairly generic way of thinking about it that I would say is worth knowing. So we get three phases. Firstly, gathering inputs, which is about if the user is doing something which you may or may not be doing, the simulation needs to know about that, needs to know if you've pressed any keys or moved the mouse or done anything. And then whether or not you do, you continue to update the simulation. And this is the part where you take all the stuff that's in your, all your objects, and you get them all to move and do stuff, right? And then the final stage is what I'm calling send outputs, and that's just where you take some aspects of the state or the behavior of the simulation and you show them to the user, because otherwise, what's the point, right? So this is just the bit where you now take the set of objects that happen to be within view of the player and you draw them. Or you take all the noises that were made in the previous iteration and you send those noises to the sound card so the player can hear them. That's basically all it is. So the obvious part of gather inputs would indeed be reading keyboard and mouse state, but there are other things that are inputs you might want to attend to at this point. Anyone want to suggest anything else apart from keyboard and mouse? Yeah? Touch, okay. Other sensors, anything along those lines? Any other modes of input that you might care about?
Joysticks.
A joystick, fair enough, yes. Could even be maybe non-obvious things like a microphone. If you had a game that had like some voice-activated element, which you could conceivably have. So those are kind of, those are all just standard input devices. But there's one other one that no one's mentioned yet. Internet. Brilliant, internet, yes. So if you're playing a network game, one of the inputs would be anything that was coming to you over the internet, which would be, either information from the server telling you what's going on, or if you're the server, information from other players telling you what they're doing as well. So it's just basically anything that's sort of outside of your particular machine. So the network one is the kind of the non-obvious but important answer there. But yeah, there's other things as well. If you had, for example, if you're doing VR, then one of your inputs would be the position of your headset. The headsets track their position in space, their position in orientation and stuff, and you need to know that because it might affect the game logic, it will certainly affect the rendering. So those are other things you need to kind of gather at some point and know what they are. So yes, other things, microphones, cameras if you're using them, stuff over the network. Anything that's coming in from file, like if you get a streaming game, you get an environment that's so large it can't stay in memory. So what you're doing is you're actually loading it off disk while you're playing. then that would actually come in through the input section. It's not a user input, but there'd be some code in there that reads streams the files that are coming in off the disk or wherever they're coming from. And another one that's very non-obvious would be seeds for random number generators, which I think of as a separate input for reasons that we'll probably talk about more later, but they can be thought of in that way. The other big input is time. This is really interesting. That when you're running a standard game, one of the things you want to know is every time you're drawing a frame, obviously each time you draw a picture and you show it to the user, some time has passed from the previous frame, and that's very important. When you're updating the simulation, you need to say, am I updating it by a 60th of a second, or a 100th of a second, or a 30th of a second? And so how do you know? Well, one way to do that is to consider time to be one of the inputs, and the gather input stage looks at some kind of system clock or something and works out how much time has passed since the previous pass through the loop, so you know how much time has elapsed. So then once you've done that, you move on to updating the simulation. What you've got there is you've got the simulation has got the state that it was in the last time you did anything. So you've got all your objects, and they've got positions and velocities and hit points and paths, route paths that they're following, whatever they've got, just the whole state of the game. And then you pass in the relevant inputs that came from this iteration, maybe the fact that the user has pressed the jump key or whatever it is they've done, and the amount of time that's passed. And now the job of update simulation is to compute what happens next. So it takes all those inputs and basically tells all the objects, okay, where are you going to be in a 60th of a second from now? By telling them to move and deal with collisions and anything else they need to do. That process in itself, that update process, might generate outputs. For example, in the case of a collision that creates like a sound output or something like that, that's the obvious one. Or there might be things that by their nature now need to be sent over the network. Like a certain player has died or something, then that needs to be transmitted to the other players so they know. Or indeed force feedback stuff. If there's certain things that if you've got like a rumbling joystick or something, you send that to the output stream so that it comes back to the player. And then finally, the send output stage is when we actually sort of the mirror of gather inputs. You kind of gather the outputs and do what you have to do with them. So you send things out to the speakers, or you send them out over the network, and most importantly, you send stuff to the screen. You draw stuff. That's a big output. Oops, sorry. Yeah, so when we're doing send outputs, actually the screen is a special case just because graphics is such an important part of the whole process and is very performance sensitive. So you don't necessarily actually do it as a totally separate phase at the end. Sometimes inside update simulation, you'll actually start drawing things halfway through because it turns out to be more efficient that way. You start sending things to the graphics card as soon as you can to speed it up. But conceptually, you could say that you're waiting until you've worked out the new state of the world, and then you draw that state of the world, even if in practice there are optimizations that mean you do it a little bit differently. And that's rendering. Right? Rendering is just the visual output state. So there's another way of thinking about this, where I'm just actually showing the flow of data a little bit more explicitly. So you gather inputs, and it returns a bunch of inputs. Those inputs go into the update simulation loop, as does the old state of the simulation, because it needs to know where it started from. So its starting state plus the inputs will generate the new state and the outputs, whatever they are. And then we send those outputs. Technically, you might just say that only needs to have outputs in it, but sometimes the output routine wants to know the state as well. For example, for reasons of rendering efficiency, you might want to have the output routine just actually know the state of the world so it can do queries that work out where line of sight intersects with objects for shadow casting and all this kind of thing. Right? And then once you do all that, you just say, okay, we're done. And now the so-called, what will be the old state the next time through becomes what was the new state this time. So this is just your kind of time has marched on. The new has become old. But if you look at this again, this is very much procedural style. These are just functions with inputs and outputs. It's not actually object-oriented at this point. So you could convert it into object speak, or you'd maybe say something like this. Just get the inputs out, and then here in the simulation, instead of passing in the old state, you just say to the simulation, look, update yourself with the inputs. The implication being that the state, both the old state and the new state, are stored inside the simulation. And that's really one of the key things about objectiness, right? You know, the objects do have internal state, it changes over time, reflects what they're doing. So the idea is that the simulation object would store the state of the world internally and mutate it as the game is playing, and it just kind of wraps it all up, so you don't need to have these state variables being thrown about anymore. And then having done all that, you do the send outputs thing, but because send outputs might want to know about the simulation state, I've kind of indicated that here by making send outputs be a method on the simulation object. So you tell the simulation to send its outputs. That way it can look inside itself to work out what it needs to do. And this is all approximate, right? This is kind of pseudo code, but it gives you the flavor of the thing. All right. So that's the core of the main loop, but there are some other things outside of that. One is you have to initialize things before you can even start the main loop. And then there's a bit of cleanup work that you do when the main loop terminates. So you wrap that around the main loop. I've suggested that you just create, a function called game, which does the initialization work where you load stuff up, load all your necessary data files, initialize the state of the simulation, do whatever kind of background work you need to do. Then you go into the main loop, and remember, this is the function that we saw earlier that is just a while loop that will eventually terminates when you quit or something like that. And then when you quit, you do this stuff, and that's when you do shutdown work. There might be resources that you need to clean up, to return to the operating system. There might be certain things you have to save or something like that just before you shut down properly. So that's most of what a main loop is like, but one thing I haven't mentioned yet, and it turns out to be important, especially for web stuff, is about events. So events are another type of input, but they're a bit different to the kind of inputs we were thinking about up till now. You can think of an event as an output that's sort of generated by the operating system or the operating environment, which for us is a web browser. So it does include the kind of things we talked about before, like mouse and keyboard events and other things like window resizing events, all those kind of things. But what's a little bit different about this is that instead of previously when you would say in your gather input stage, you'd be able to do things like gather inputs would simply look at the state of the keyboard, what the keyboard is represented somewhere in the computer, and you could say, have they pressed the W key, that kind of thing. So you ask the question when you're doing gather inputs. But the way events work is they get pushed in instead. So with events, what happens is something outside of your app, like the web browser or the operating system, it detects that a key's been pressed, and it passes that to you, and you now need to handle it. So it's just a slightly different way of thinking about it. It's just a push versus pull scenario. So the way events work, as I said, they push information into your program, particularly information of the kind that the program itself couldn't pull, stuff that maybe for reasons of security, your app doesn't actually have access to it. You're not allowed to maybe directly read stuff from the network device, maybe you're not, in which case you'd have to wait on the operating system to tell you that it had arrived and to make sure that it only sends you the things that your app is allowed to see, so you can't see other people's network traffic. So that's sort of what I'm saying there. The other thing you have to remember about events is there's kind of a convention where events are seen as being quite high priority, and that it's the obligation of your app is to respond to the event as quickly as you can to keep the whole system running. And in particular, if you don't respond to the events, the OS might interpret that as a sign that your program is misbehaving, and it could actually terminate you. You'll have no doubt seen on Windows that sometimes you'll get this application is not responding, that kind of thing. That's usually because the operating system there is pumping events into the app, and the app isn't reading them, so the event queue is just getting longer and longer, and the operating system thinks, oh, this app isn't behaving itself, it's not going to respond to mouse clicks, which might mean the user might be trying to click the X button to close it, but the app isn't reading the event loop because it's busted, in which case you can't close the app, so the OS jumps in and says, you want me to kill that for you? So they generally interpret not reading events as a bad sign. So it's important that if you do have an event stream in your app, you respond to them kind of quickly. So the upshot of this is that you have to just extend the main loop a little bit with some event handling stuff. And here's the way I've suggested doing it. That I'm putting one extra layer above the main loop, which is just that before you go into the main iterate part that does the gather input, simulate output thing, you do this other thing where you handle the events. And this is where you process OS stuff at a high priority. And you'll see this in other systems. If you ever write an app for like Windows or something, you'll actually see this when you write WinMain. You have to write a little event loop thing before you call the main part of your app. And that's all I'm describing here. But what's interesting about the browser is that in the browser, almost all of your inputs come in the form of events. You can't really do things like just reading the state of the keyboard. It's not the way it works in the browser. You don't say, is the Y key down right now? What happens instead is when the Y key is pressed, you get a Y down event, and when it's released, you get a Y up event, and you just have to track those that way. That's kind of how it all works. All right, so having explained the main loop, there are a couple of things I could do. I could, of course, just go through in order, start with inputs, then do the simulation, then do the output, or I could start in the middle, why not, do the core of the simulation, because that's like the interesting part, I guess, or the central part. But what I've decided to do instead is to start at the end, do it completely backwards, and talk about rendering first. One of the reasons for that is that if you were trying to reverse engineer a system, if you're trying to figure out how something worked, that's the outputs are the thing that you can see and you can think about. You can kind of say, well, okay, no matter what happens at the end of the game, we end up drawing, a city and some cars and some guys, and that's what we see. So let's think about that and work backwards to figure out how it got there. That was one reason. Also, it just turns out, in terms of structure and material, it seemed practical to do it this way. So that is actually all I have to say. The main loop introduction is fairly short. So this is not a full lecture slot. That was only like 20 minutes. So I'll just take a very brief pause here and we'll just roll on to the next part.